Okay, good morning, everyone. Hope you all had a nice weekend. So a couple announcements as we get started today. Number one, hopefully you all saw the announcement that I've had to change my office hours this week. So I will have my normally scheduled office hours this afternoon from 1 to 2:30. I will also have office hours Wednesday afternoon from 1 to 2:30, but I will not have my normal office hours Friday morning. And that's this week only. I hope that doesn't cause a major inconvenience, and I apologize in advance if it does. Second thing, you might also have seen the announcement yesterday that grades for Homework 1 have now been posted, as have comments and whatnot on your choices of technology for your term paper. I went through all of those over the weekend. If you submitted something, there are comments left for you. In many cases, the comments are as simple as technology approved. I thought what you wrote was fine. There's no action necessarily needed other than just start working on your term paper. There are a handful of people where I did either request a little bit more information just to make sure there aren't going to be problems a little bit down the road, or in certain cases, a few people picked technologies that I don't think are particularly good choices or are too close to what we're going to do in lecture. And I left comments there as well. So please take a moment in the next couple days, look at the comments, and if I've asked for more information, please send it to me. Let's not let this drag on, and don't send me an email the day before the term paper is due saying, "Oh no, professor, I didn't realize my technology didn't get approved. What do I do?" I don't know the answer at that point. So please take a look. And remember, so if you look at just sort of the grading center and you see you got 20 out of 20, that does not necessarily mean your technology was approved. That means you submitted it on time and answered the questions. Okay? So don't look at the grade as necessarily thinking the technology was approved. The two are completely unrelated. And just as a note, I also know there are a few people that didn't submit a choice. If you submit a choice by this Friday, it won't get credit because it's late, but I will still give you comments. Anything submitted after this Friday will be returned without review. Okay, any questions on that? Okay, and then just the last announcement, Homework 2 was posted Friday on the unit. We're going to get probably the lion's share of the way through the rest of the material today, but we probably won't quite finish it until Wednesday. So that homework will be due this time next week on Monday, and we'll have the quiz the following Wednesday. Okay, any questions on that? All right. So then the last thing, you might have seen me futzing with the computer here at the beginning of class. The smartboard is not working today. My marker is not working at all. So I apologize. When we need to go to examples, we're going to have to put the projector up and bring the whiteboard down, and that's going to be a bit of a pain. I've already submitted a service ticket to AV, so hopefully that will be fixed for Wednesday. And I, again, apologize in advance that that's going to be a little bit weird. So, any questions on material before we jump into some new stuff today? Okay, so what were we discussing last time? I know it's been a while. Yep?
Converting a decimal number to binary.
Right, so we were discussing binary numbers. And so what was the main question? What were we really trying to get at with these binary numbers? Was this just something we were doing because we were feeling thrifty, or was there a purpose? Right, so the idea was we're talking about digital devices, computers, smartphones, tablets, and in particular we saw last time when we discussed memory and processors and how these machines worked, that they store everything in terms of zeros and ones, in terms of on and off. They process all information as zeros and ones. And so if we're wanting to think about how does a computer work, we have to first figure out how do we store things as zeros and ones. We have to take all of these objects that we are used to working with as human beings, Word documents, websites, spreadsheets, movies, music, any of these different types of things, and somehow convert them to a sequence of zeros and ones in order for your computer to store them or to process them. And so I mentioned last time when we started this discussion that we were going to spend a bit of time looking at numbers, in particular non-negative integers, which is what we spent most of the last class period looking at. And so we started with sort of these examples here of just what are some numbers, and we had 0, 1, 2, 14, 179, and how do we convert it into zeros and ones. And what we spent most of the lecture period looking over was this idea of the binary number system, which was to say base 2. So we're used to working in base 10 as human beings. When I said 179, those three digits, that 1, that 7, and that 9, the 1 we know says that's how many hundreds we have. 100 being 10 squared. The 7 was how many 10s we have, 10 being 10 to the first. And the 9 was how many 1s we had, 1 being 10 to the 0. And so the whole idea that we discussed last time was there's nothing, absolutely nothing special about using 10 as that base. We could just as easily use 2, which would give us what's called the binary number system. And we spent the rest of the class period talking about how do we convert back and forth. How do we take something that's written in decimal or in base 10 and convert it to binary? And how do we take something in binary and bring it back to base 10? And why might we be interested in both of those operations? Why might we need to go both ways? Why might we need to go from decimal to binary? Right, so we can input something in the computer. If you're in Excel and you need to put the number 179 into one of the little blocks, do you have to convert it to binary, or do you just type 179? You just type 179, and the computer does that transition for you, because it's going to store it in binary. Likewise, after the computer's done some operation and it gets, I don't know, the number 1,719, does it print out that number in a whole bunch of ones and zeros, or does it then convert it back to decimal to display to you? It's going to convert it back. And so this operation is going on under the hood all the time when we're working with computers and with numerical information. And so what we spent the last time was sort of discussing how does all of this work. We went through a whole bunch of examples on how to do it. And the key idea is we can ultimately get this expansion where now we're going to say take our number in decimal, 179, and write that as something times 128 being a power of 2, plus something times 64 being a power of 2, plus something times 32, and so on and so forth. And the trick is figuring out what are these coefficients that go in front of all of these powers of 2. In the binary system, they're either a 0 or a 1. And the way that we ultimately get our binary number is to just sort of read these coefficients out in order. So we can say here's a 1, 0, 1, 1, 0, 0, 1, 1. And sure enough, that's how we represent the 179 in binary. Okay. So I think this is where we left off last time after going through a couple examples. And so what I want to do, sort of to bring in the math concept maybe a little bit more strongly, is then ask the question, so last time I asked, was there anything special about base 10 and the decimal numbers that we're used to working with? And of course the answer was no. So we introduced base 2, because that was something that's going to be convenient for us to use with computers. Now I'll ask the question, is there anything special about base 2? No, there's not. And so what ends up happening is this generalizes very nicely to have a whole bunch of different bases. We could think about working in base 3. We could work in base 4. As I put on the slide here, we could work in base 3,972,832. I don't know anyone who's ever used that base. I don't think it's particularly instructive. But could we? Yeah, we could. And so what's sort of the common theme? If we're thinking about now these base systems and how to represent these non-negative integers, what do you think the trick is going to be? What's the importance of the base? Any thoughts? Okay, let's take a look and find out. And just as a note, oftentimes when working with computers, base 16 is common, not because the computer actually necessarily uses it, but it's very easy to go back and forth between binary and base 16, and it makes a slightly more readable version for humans in some cases. Anyway, so what we can do is look at the different patterns. So in base 10, we could take a number like 25, and we could write it, again, as some number, in this case 2 times 10 to the first, plus some number, in this case 5 times 10 to the 0, and we would denote that then as 25 to be our particular number. In base 2, we would go through the exact same idea, but instead of using powers of 10, we're going to use powers of 2 when we write out that expansion. And so if we wanted to write write 25 in base 4, what do you think it is that we're going to have to do? We're basically going to have to do the same thing, only we're going to write it in terms of powers of 4. Okay. And so if we wanted to think about this now, so what we need to do then, first of all, is think about what are our powers of 4? What's 4 to the 0? That's just 1. What's 4 to the 1? 4. And what's 4 squared? 16. Okay. What's 4 cubed? Does anybody know off the top of their head? 64. Okay, so we're looking at 25. Are there any 64s in 25? No, there aren't. So do we need to worry about that power? Nope. Are there any 16s in 25? Yeah. How many 16s do we have? We've got exactly 1. Okay, so we can write 1 16. When we subtract off the 16 from 25, what do we have left? 9. So we come down now to our next power of 4, and we ask, are there any 4s in 9? Yeah, how many do we have? We've got 2, so we can put a 2 there. And if we subtract off, well, 2 times 4 is 8. And we remove that 8 from 9, what are we left with? 1. And are there any 1s in 1? Yep, there's exactly 1, so we put a 1. And notice we have this 1, 2, 1 as those coefficients. And sure enough, that's exactly how we would write 25 in base 4, as 1, 2, 1. Does that make sense? Okay, so the common theme, if we're thinking about other bases, is when we're going to use base n. Where now n is, 2, 3, 4, 5, 17. First of all, does it make any sense to choose 1 as our base? Could we have a base 1 number system? Why would that maybe not work? Right, because all the powers of 1 are 1. Okay, so we need our base, our n here, to be at least 2. It's not going to work if we use 1. Okay, so the first thing we can do once we have our base n is we need to look at what are the different powers of n. So n to the 0 is a freebie because that's just 1. And n to the first is a freebie because that's just n. Okay, then n squared, n cubed. Maybe this requires a little bit of work. But once we have those, cool. So second step is we need to find the largest power of n that's smaller than the number we're looking to convert. So in our last example, when we were looking at the number 25, that biggest power of 4 that was smaller than 25 happened to be 16. Okay, and that's where we started our expansion. And so then basically spelled out here is exactly what we did. How many of that power do we need? Okay, we can figure that out and put in that digit. We subtract off that amount and continue with what remains, just working through and looking at each of the successively smaller powers of n. And so maybe for the last question that we have then, what are the actual digits that we need to use? So we know from 20 years of experience, when we work in the decimal number system, what are the possible digits that we can have anytime? When we're talking about how many hundreds we have, or how many tens, or how many ones, what are the digits that we can use? 0 to 9. In particular, there are how many of them? There are 10 choices. When we had binary last time, what were the possible digits that we could have? 0 or 1, which is exactly 2. And so this is what happens. In general, if we're going to use the base n number system, then there are n possible digits, going from 0 to 1 to 2 up to n minus 1. So from our example in the last slide of base 4, what are the possible digits we could have for any one power of 4? 0 to 3. Okay. Now the trick in where this gets a little bit fun is what if n is greater than 10? What if we're using, let's say, base 16, that hexadecimal, hexa for 6, decimal for 10, 10 plus 6 is 16. If we're using that hexadecimal, what might we use if we actually needed to put the digit 10 or 11 or 12 or 15 in one of those spots? Are we going to literally write out 1/5? Or is that going to cause more problems down the road than it's worth? That's probably going to cause problems. And so by convention, what we do is we'll use letters to replace those numbers. So if we were going to work, let's say, in base 16, and we needed a digit 10, we're going to use the letter A to represent that 10, and B for 11, and C for 12, and so on and so forth. What happens if we run out of letters and we get past Z? I don't know. I don't actually know anyone that uses base 37. I don't think there's convention for that. But this is up to at least base 36. This will get us there. Okay? And again, if you're curious or you have other questions, there's a link here for the Khan Academy that has a really nice discussion of these ideas. And so maybe let's jump in with an example. How can we convert the decimal number 233 to base 16? Why don't you take a minute and see if you can compute this out, and then we'll talk about it as a class. And while you do that, I'm going to transition over to the whiteboard. First of all, can everyone see the whiteboard at least somewhat okay? All right. If it becomes an issue, just scream at me. Okay, so does anybody have an idea where would you start? If we wanted to convert 233 to base 16, where do we begin? Right, so we need to figure out, first of all, what are some powers of 16? Because we need to find the biggest one that's smaller than 233. Okay, so 16 to the 0 is, do we have any, yes, so 16 to 0 is 1. Do we have any 1s in 233? Yeah, okay, let's keep going. 16 to the first is 16. Do we have any of those? Yep. And what's 16 squared? 256. Do we have any of those? No. Okay, so what we know is that 233 now is going to be equal to something times 16 plus something times 1. So what we need to figure out now are what are these two somethings. How can we go about figuring out the first one? I'm sorry? Wait. Right, so we can divide 233 by 16 to determine how many 16s are there in 233, and we get 14 of them. Okay, so I'm going to write that just right here for a moment. Can we actually put 14 in this blank? No, because then it would look like that's actually two digits, a 1 and a 4, and that could be confused as saying there are 4 16s and 1 256. Okay, so instead we're going to do what? We're going to use a letter. And which letter do we put in for 14? It's going to be E. Okay? Because if we think about sort of putting a little table here, A is 10, B is 11, C is 12, D is 13, E is 14, and F would be 15. Okay. So now, what are E16s? How much of the 233 does this account for? It's 224. Okay, so we need to figure out now what's left to be able to figure out what's over here. And so we can take our 233, what was it, minus 224? And we get 9. Okay, so then we ask ourselves, are there any 1s in 9? Yes, and how many? There are 9 of them. So we can put a 9 in that blank. And so to represent 233 in base 16, it would appear as what? E9. Who likes the number E9? Okay. Where this can stay. If this falls off and hits me, David, come up and continue the lecture. Okay. So something else that we can do that might be a little bit weird is we can consider the example what number is facade? Okay, first of all, is that a word or a number? It could be both. Okay, but in particular, if we want to think about using the hexadecimal number system, in base 16, this is a perfectly valid number. Okay? So what number in base 10 does this represent? I'll give you a hint, it's not a small number. Okay, well, while you work, I guess I'll start working on it here on the board as well. But I'm going to erase this just to get a little bit more space. Okay, so the first thing we might want to do is figure out what are the actual powers of 16 that all of these digits correspond to. And again, keeping in mind from last lecture, usually we're going to want to start at the right when we're figuring this out, because that rightmost digit is going to be 16 to the 0, then 16 to the 1, 16 squared is 256, 16 cubed is 4,096, 16 to the 4th is 65,536, and then our last digit out here is the 1,048,576's digit. Okay? So once we've got that, the other thing we need to then do is figure out how many of each of these do we have. So the E here, all the way down at the end of facade, represents how many?
14.
That's 14. So we've got a 14 for that. The D represents 13. Okay, so this is telling us we had 14 ones. We've got 13 16s. A signifies 10, so we're going to have 10 256s. C tells us we have how many 4096s? 12. Another A in the 65,536's digit tells us we have how many? 10. And lastly, the F in the loosely 1 million's digit tells us 15. Okay? So we can now multiply all of these out. And starting, I guess since I'm at the left side of the board, this gives us 15,728,640 from that F in the loosely 1 million's digit. This one's maybe a little bit easier. We're going to get 655,360 from the 65,500's digit. And our next one is going to give us 49,152 from that 4096 digit. 2560 from our 256's. 208 from our 16s. And how many in our 1s? 14. Just 14 times 1 is 14. And now what do we have to do to all of these numbers? We need to add them up. And when we do that, has anybody gotten the answer? Yep. Exactly. So we get 16,435,934. So if you're wondering what number facade represents, assuming it's base 16, we would get loosely 16.5 million. This can also be something, as a side note, of a weird and strange geek game, but trying to figure out how many different things can you represent using just hexadecimal characters. So maybe using numbers in creative ways and then the letters A through F. Some of my favorites are feed beef to face. can do that all with A through F and the numbers and sort of figure out what sorts of numbers can you represent that look kind of funny in English. But anyway, that's neither here nor there. So let's switch back to the projector. Give it a moment to power back up. I apologize for this again.
When it comes up, can you go back to the slide with the rules of other bases?
Yeah, we'll do one thing here and then. Okay, so I've skipped ahead a few things here, but one of the things we can see, so there's the examples. You can see the answer there. The other nice thing is, remember, Wolfram Alpha can again handle a lot of these base conversions for you. And so you can come in and say, put facade from base 16 to base 10. Again, look at your input interpretation to see that it says, oh, facade, I recognize that as a valid hexadecimal number. Convert to base 10, and it'll spit out the answer for you. Again, a great way to sort of check your work. You wanted to go back to the
rules of other bases.
Yep. So we have the rules for other bases, these here. And so that's exactly what we did the last time. Again, we had to figure out with the facade, or with these, what was that largest power of 16 that we needed? And then it was a matter of just figuring out how many go with each of those powers. Okay? Any questions on those two examples? Yeah. Right, if you're using numbers less than 10, you're just going to stick with the 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. But yeah, when you go to 10 or higher, then you would start saying 10 is A, 11 is B, and so on and so forth, just to avoid ambiguity. Yep. Yep.
So with the letters, like, could it go all the way down to Z? So I guess Z would be like
36. Actually, excuse me, Z would be 35. Yep. I don't know anyone that's ever used a base system that large outside of just being a jerk in a class and giving you some pedantic, esoteric exercise, which if you've looked at the homework, I did not. At least not in this context. Okay. Other questions on this? Okay, so I just wanted to show you briefly sort of what these number systems and these base systems are. Just again, to sort of show, here's one of these math concepts of different ways that we can represent this. Base systems sort of being one class of what's called representation theory. Okay, and how do we actually represent this idea where the concept is the number 25, and how do we talk about it? We could say it's 121 in base 4, it's 25 in base 10, and so on and so forth. There are lots of different ways to see that. Okay, so what we now want to do is we can recap, at least thinking about our computer examples and heading towards digital devices, is that what we've seen is that non-negative integers can be turned into sequences of zeros and ones using binary numbers. We don't need to go through that again. And so as sort of one practical matter, is your computer memory or your hard disk unlimited? Do you have an infinite amount of storage space? No. So is it possible for your computer to store any number, non-negative integer? No. There's going to be a limit. And so this starts to be actually a really important question when companies like Intel and AMD are designing their chips and their processors, which is to say, how much space do we actually allocate for numbers? Because we have to assume at some point there's just some finite amount of space, and how do we treat it? And so suppose, just for an example, that we only allocate 8 bits to store our number. How would we store the number 357? What was that? Nope. So the question was, does that mean we have to do it in base 8? Remember, computers can only store ones and zeros. Well, what we're saying here is that we're allocating 8 bits so we can have a sequence of 8 ones and zeros, and that's all we have to work with. How would we store 357 in those 8 bits? Nope, we're working with base 2. Computers always work with base 2, so we don't need to figure out what base we're going to work with. We're working with base 2. What do you think? How do you think we could go about trying to tackle this question? I'll give you a hint. It might be a trick question. You can't. Why can't we store the number 357 in 8 bits? Yep. Right, we don't have enough powers of 2. If we were to convert 357 to binary, does anybody recall or have a guess what's the biggest power of 2 that we're going to need? It's going to be 256, which is 2 to the 8th. Remembering that the very rightmost bit of our number is 2 to the 0. Okay, how many total powers of 2 does that mean? We need 9. So if we only have 8 bits, can we store this number? No, we can't. And this is, in practice, something that you might have to worry about if you were a computer engineer and you're designing how these chips are going to work. I don't want to say much more than that, but I just wanted to alert you to this fact that, again, even though this works great in principle, we can take any non-negative number and we can convert it, in practice there are limitations, just because the computers at some point have to make assumptions over how big things are just from an engineering and logistical perspective. Okay? So, what I now want to do after we've spent almost an entire class period between last time and today talking about non-negative integers is to take a really radical step and think about negative integers. I know you're wondering, how is this going to get to Word documents and pictures and movies and all that? I promise, when we get done with numbers, things start going really quickly. So how can we think about non-negative integers? Does anybody have an idea? How can we convert non-negative integers to zeros and ones? Yep? We could keep on subtracting. That's true. The issue that we might run into, would we ever stop? Because you might need to keep just subtracting. And again, we want to try to keep this in as finite and as small of a space as possible. So that's a good thought, but I don't think in practice it's going to be quite the way we want to go. Other ideas? Yeah. Okay, so maybe there's a symbol that we put in front of the coding. That's a great idea. And that's actually the first thing we can discuss. So if you notice, excluding 0, every integer is either positive or negative. Okay? Which is to say there are exactly 2 options. Well, if we have exactly 2 options, that sounds something like something that's what? Binary. So could we just put a bit in front of our number and use that as a sign bit? Okay, so think here in the example, we're looking at the number, what is this, 13? Well, what we saw from 13 before, if we had just the positive integer 13, would be 1, 1, 0, 1. 8 plus 4 plus nothing in the 2's plus 1 is 13. We could put a 0 in front of that. So that's this red 0 here on the left, where maybe 0 signifies that the number is positive. Likewise, if we wanted to store negative 13, maybe what we could do is put a 1 in front of that digit, in front of that number, where that leading 1 tells us that the number is negative. Does this seem like a reasonable approach? Yeah. Question? Yes, but that's exactly what we're trying to do. Because we're trying to figure out how do we store both a positive 13 and a negative 13. And so, yes, these 2 are different numbers because under this convention, that 0, 1, 1, 0, 1 would be positive 13. And the 1, 1, 1, 0, 1 would be negative 13. Again, coming back to the meaning of what does each of those bits, when we read out this sequence of 1s and 0s, what does each bit mean? And so in this case with the sign bit, that first bit tells us positive or negative. Maybe 0 is positive and 1 is negative. The next digit in this case is 2 to the 3, 2 squared, 2 to the 1, 2 to the 0, using our binary numbers from last time. Does this seem like a reasonable approach for dealing with negative numbers? Is it fairly compact? Did we have to add a lot of information to deal with plus and minus?
So that means that we could assume that in every computer that's coding, I guess, that the first number is always going to represent positive.
Okay, so could we assume that in computer and all this, that first number is going to represent a sign bit? No, we're going to find out this is actually a really bad idea. But what I'm looking at here is from the problem-solving approach, does this seem like a reasonable idea at first blush? Yeah, it doesn't seem to be that bad. It only adds 1 extra bit. And we can this now store all of the integers? Sure, we can handle all of the positives, we can handle all of the negatives, and even that one that's neither. Can we handle 0 using this approach? Yep. Okay, so now, let's go on to the next slide and discuss why this is actually not a particularly good idea. First of all, it's redundant. We can store 0 in 2 different ways using this system. Because think about it now, the binary representation for 0 would just be 0, 0, 0, however many bits you've got. And we could put the sign bit in front of that just like we would any other number. Well, is there really a difference between positive 0 and negative 0? Or are they both just 0? Okay. So that's sort of a problem because we just sort of talked about space is limited. We've got a finite amount of space to work with. Do we really want to use a system that says we have 2 different ways to say the same thing? That seems kind of wasteful. Would anybody agree? Okay. Point 2 here is actually the bigger problem when dealing with how the computers work and process this. And it's the idea that addition actually becomes very complicated when you use this sign bit. And so suppose we wanted to just consider the example negative 13 plus 1. Okay, naturally the answer is negative 12. That's what we would expect. And so we want to look at this, but now if we go into the binary arithmetic, this becomes complicated. So what we can do, and let me see if I can just use the mouse to point here, and it's a little bit too tall for me. So we have now minus 13 using the sign bit would get stored as 11101. Again, that leading 1 telling us it's negative, and the 1101 specifying 13. Our positive 1 would just be 0001. Again, that leading 0 telling us positive, 0001 telling us 1. And if we were to add these 2 numbers together, we would expect, as human beings, negative 13 plus 1 is negative 12, to get negative 12, which is represented as 11100. But if we actually add those 2 binary numbers together, the 11101 and the 00001, what do we actually get? We get negative 14, because we're going to get this number here instead. So when we go through, think of this as the normal addition, but 1 plus 1 is 0, carry the 1, sort of keep going over. And so we end up getting this 11110, which represents negative 14. So what we've now done using this simple binary arithmetic, which is something we would really like to have working, that's something we can make computers to do really, really well. We take minus 13, we add 1, and we get minus 14. Does that seem like a good idea? No, that seems sort of problematic. And if you think addition was this complicated, what do you think multiplication is going to look like? It's looking like we probably want to go back to Roman numerals at this point. Okay, so the sign bit is an interesting approach. It was certainly one of the first ideas that was proposed for how to deal with negative numbers in this case, but it seems it's actually probably not the right way to go. And I'll ask the leading question, which you can probably infer the answer is yes, can we do it better? Okay? And so the answer, and this is what the computers now actually use in practice, is this idea called 2's complement. Okay? It's a pretty straightforward idea. It's a little bit tricky to work with in practice, and we're not going to go into a lot of detail on it. But basically, what ends up happening is we're going to bring with us all of our discussion from non-negative integers. So everything we did last time and at the beginning of lecture today, we're still going to be doing. And compared to the sign bit, what we're going to say now is there is no dedicated sign bit, which is to say we are not having one bit whose exclusive purpose is to say positive or negative. We're going to have a bit that functions as a sign bit, but that's not going to be its only use. And so where 2's complement comes in, and this is the big caveat, again, keep in mind this picture, when we're talking about a sequence of 1s and 0s, what does each 1 or 0 tell us? What is it meaning? When we had our binary numbers from last time, if we were to take something like 0101, what those are telling us are the coefficients in front of all of these successive powers of 2. When we want to go to 2's complement, we're going to make one change, and one change only. And that's to say whatever the leftmost bit is, so in this 4-digit case, that 2 to the 3rd digit, is going to be negative. So instead of representing how many 8s we have, in this case it's now going to represent how many negative 8s we have. Okay? And so one of the key caveats now, if we're going to use 2's complement, do we have to know precisely how many digits we're using for our number? Yes. Because however many digits, that leftmost digit is going to have that negative sign thrown in front of it when we do the expansion. So if we're using, in this case, 4 digits for our number, that implies we have a negative 8. If we had 5 digits, okay, so we added another digit to the left, is the 8 going to be negative or positive? It's going to be positive, and the 16 will then be negative. Okay, so that's one of the takeaways from 2's complement. We have to know how many digits we're working with. Okay, and so now notice here, in this example, we had 8 was the negative. If we were, suppose we had a 1 in front of the 4's digit and a 1 in front of the 2's digits. I know it says 0 here for this example, but suppose that was a 1. And we had a 1 here in the 1's digit. What number would that give us? 4 plus 2 plus 1 is 7. Okay. So if we were to put a 1 here on the -8, the resulting number always has to be negative. Okay? Because excluding this bit, putting all of the 1s on all of these positive parts only gave us 7, but having 1 on the -8 will always give us more negatives than positive. So that front bit still ends up working as a sign bit. You can tell from 2's complement, look at that left digit. If it's 0, we're non-negative. If it's 1, we're negative. But it's not just dedicated to the sign. It has this double meaning of saying, well, that's how many negative whatever that power of 2 is that we have. Does that make sense? We're going to do some examples on the next slide. But that's the general idea of 2's complement. And the reason why this ends up working is that the binary arithmetic, if we now want to add 2 numbers, do you think this is going to give us what we want, or do you think this is going to be equally weird? So if we took the 2's complement representation for -13 and we added to it the 2's complement representation for 1, what are we going to get? What do you hope we get? -12. And it turns out that will indeed be the case. So this system for storing the numbers is going to make addition and all of these other operations much nicer. So for the examples, if we wanted to think about a 3-bit 2's complement, again, we have to specify how many bits we're using. This 0, 1, 1 up here at the top is specifying, well, what does that 0 represent? What power of 2 would we associate with that bit? It's a 4, but if this is 2's complement and that's the leftmost digit, it's not going to be a 4 but a -4. The middle digit tells us how many 2's, and the right digit tells us how many 1's. So what this is saying is 0 -4's plus 1 2 plus 1 1. And so if we have 0 times -4 plus 1 times 2 plus 1 times 1, that gives us 3, which is what we can see. And likewise, if we were to come down here and look at this one, so that leftmost 1 tells us we have what? A -4. The zeros tells us how many 2's? 0. And that last 1 tells us we have a 1. And so -4 plus 1 is -3. Okay, and so what we can now notice even, if we were to take our 1 0 0 here for -4, and we add 1 to it, we get 1 0 1 in the binary, which is -3. And if we added 1 to that, we get the 1 1 0. Again, the 1 plus 1 is 0, carry the 1, which is -2. And now, -1 has this 1 1 1 value. If we add 1 to that, what happens? It flips to 0, so we would first have to say 1 plus 1 is 0, carry the 1, plus 1 is 0, carry the 1, plus 1 is 0, carry the 1. What happens to that 4th digit that we should be putting that extra 1 in? It gets lost, because our computer's saying we're working in a 3-bit system. We only have the 3 spaces. We need that 4th one. It's just gone. Something called overflow in principle. But in this case, it actually now gives us the behavior we want because the 3 digits that remain are 0, 0, 0, which just happens to correspond to 0. And so what that's telling us is -1 plus 1 is 0. Exactly as we would have hoped and exactly as we would have expected. Okay? So let's do an example again using 5-bit 2's complement. How would you represent 5 and or -5? Okay? So why don't you take a moment to think about that. I'm going to clear the board off and then we'll work it through together. Okay, well, if we're using 5-bit 2's complement, how many different bits do we have in our number to store 5? We're going to have 5, okay? And so we know what we're going to need to say is now 5 is equal to some leftmost bit. And what is this one going to represent? It's not quite 2 to the 5, it's 2 to the 4th, but is it positive or negative? It's negative because we're using 2's complement. That leftmost bit will always correspond to a negative power of 2. So we're going to get negative 2 to the 4th. Our next bit, what's our next smaller power of 2? 2 to the 3rd, and do we want it positive or negative? Positive, because only the leftmost bit is negative. And then continuing along, plus, something times 2 squared, plus something times 2 to the 1st, plus something times 2 to the 0. Okay, so what we now need to do is start filling in these digits. Well, is this number negative? Is 5 negative? No, so we immediately know what digit has to go in this leftmost bit. It has to be a 0. Okay, so remember, we saw that this ends up functioning like a sign bit, even though it's not dedicated to that purpose. But a 0 leading this number tells us it's non-negative, and a 1 would tell us that it is negative. Okay, so we know immediately there's a 0. Okay, and so now we can sort of proceed through. This is now just binary numbers. How many 8s do we have in 5? 0. How many 4s do we have in 5? We've got 1. When we subtract that 4 out, we're just left with 1. Okay, are there any 2s in 1? Nope. And are there any 1s in 1? Yep. And so if we now read out these digits, the number 5 in this 5-bit 2's complement is going to be 0, 0, 1, 0, 1. Okay? Does that make sense? So let's consider the other way around now. We'll clear these digits out. And suppose we wanted to use -5 instead. Okay, well, the idea is exactly the same. We're now going to want to say -5 is equal to something times -16 plus something times 8 plus something times 4, something times 2, something times 1. And so again, we start. What do we know the bit has to be at the very left end here? It has to be a 1 because -5 is negative. Okay, so we put a 1 there. Here's where this gets a little bit weird. So what is this? This tells us we have a -16. Okay, so now what we need to do is figure out what do we need to add to -16 to give us -5. Okay, You're right. The idea is 11. And the way that we can see that, think about adding or moving this negative 16 over to the other side. And what we can end up getting is that 11 is then equal to the minus 2 to the third plus dot, dot, dot. Okay? Does that make sense? Because we can, if this is the equality, we can always just move this constant term over and figure out now what's the positive number, or at least non-negative, that we need to get the rest of the digits. So we can then ask ourselves, how many 8s are there in 11? Is it 11? Yeah. There's 1 8. And when we take away that 8 from 11, what are we left with? 3. Are there any 4s in 3? Nope. Are there any 2s in 3? Yep, there's how many? 1, which leaves us with 1. And are there any 1s in 1? Yes. And so what we end up finding is that our negative 5 and 5-bit 2's complement is going to be 1, 1, 0, 1, 1. Okay? Question? So if you don't have enough bits to do it, then the computer just can't handle it. And so it just can't store that number. And so what the computer will usually do is say, so we had that example, what was it, 357 and 8 bits? It would maybe calculate out what is that binary expansion, then anything after those lower 8 bits. So it'll keep the 1's term, it'll keep the 2's, the 4's, the 8's, and so on. It just chops off anything that remains. So whatever that 256-bit was is just gone. Is what usually, that's not necessarily, I believe, required, but that's what usually happens in practice. The idea is you typically don't want that happening. You want the number 357, not something arbitrarily smaller. Okay? All right, let me see what's next here, whether we want to stick with this or not. Okay, yep, so we will come back to the projector. And so there's a quick example here in the lecture slides as well of taking something from 5-bit 2's complement, converting it back to base 10. I'll let you work that out on your own time. Yep.
Where did that 11 come from?
So the 11 came from, so remember we had, if I sort of duck under here, this very first term, nope, sorry, that doesn't bend. There was this 1 times, maybe you can see that briefly, 1 times there was a negative 16. We can move that over to the other side. And so when we add 16 to both sides, that gets rid of it over here, puts it over on the left, and 16 plus negative 5 is 11. Yep. Okay. And so like I said, there's this other example. If you wanted to see how to go from 2's complement to base 10, just expand it out. So in this case, we had this 1, 0, 1, 0, 1. The 1 tells us we have what? A negative 16. Do we have any 8s? Nope. Do we have a 4? Yep. Okay, negative 16 plus 4 is negative 12. Do we have any 2's? Nope. Do we have any 1's? Yep. Negative 12 plus 1 is negative 11. There you go. That's all that's going on there. Yep.
So from now on, are we going to just use the complement only when it has?
So I will try to be as clear as possible. If it doesn't say 2's complement, you can assume it's probably just a binary number. But if it's unclear, please ask. Yep. All right. So that's how we deal with negative numbers. I told you we were going to start going a little bit more quickly. Now that we had non-negative numbers, that took a while. Negative numbers, there it is. How do you think we can start to deal with non-integer numbers? Can anybody think of a non-integer number you might want to store or might want to use on a computer? Pi. Great example. Might we want to use pi? Yep. How do we go about that? Well, so what ends up happening is that we can try to convert these numbers, or at least approximately, into binary form. And so one of the issues that we have to start dealing with is the idea of rational numbers versus irrational numbers. So pi is is it rational or irrational? Irrational, and what does that mean? It can't be expressed as the ratio of 2 integers. Okay? Or equivalently, it's a non-terminating, non-repeating decimal. So you get 3.141592.6. It goes on for a while. Okay, and so exactly there it is. I guess I should have stopped at 2.7. My apologies. Anyway, what ends up happening is if the computer wants to work with pi, the trick is it's going to have to truncate it somewhere, because pi is infinitely long, which is to say there's an infinite amount of information to be stored. Can a computer store an infinite amount of stuff? No, it can't. So we're going to have to approximate it. Okay? And the idea is, do we necessarily need infinite amount of precision? When you were having to work on some of the GPS stuff and we had sort of a pi or a 90 degrees, on the quiz last week, did I ask you, did you have to give your answer to an infinite number of decimal places, or was it good enough to go to the 10th digit? So if we know we only care about going to the 10th digit, are we going to need pi to a million decimal places? Probably not, maybe 3 or 4. In fact, that's probably more than enough. And so the idea is we can start to approximate this, given that we know we're working in some limited amount of accuracy. So long as our number is good enough to meet that end goal, who cares? Okay? And so what we can find is that there are always successively better approximations to pi. So how many of you maybe in middle school saw that like 22/7 was approximately pi? Does that ring a bell to a lot of people? A little bit? Okay, so we can take the expansion from 22.7 and realize we get the 3.142. Okay, well, so that gave us 3 digits of accuracy. If that's all we needed, that's good enough. We can do better. 355 divided by 113 actually gets us, what is this, 7 digits of accuracy. We get the 3.141592. And we can do better. You can keep finding better and better and better rational approximations for pi, depending on how much accuracy you need. And there's a website here if you want to see a whole bunch of them. So the trick is, if we're going to talk about non-integer numbers, if they're irrational, just approximate them as a rational number. And what do you think we might do if it's rational? Good. You've got a homework problem to explore this a little bit. So I'm actually not going to tell you in lecture. I want you to think about it. Don't worry, I give you a good hint. But if we can now look at positive numbers, negative numbers, and non-integer numbers, are there any other types of numbers we really need to worry about? Or does that pretty much cover the bases? That's pretty much it. So that's how we do numbers. Congratulations, we've made it through the worst part of this unit. Now, what are some other things you might like to store besides numbers? What was that? Letters. Okay. Who likes to put text or use text or words or things on their computer? Okay. So how might that work? First, we have some comic relief. I like the one on the bottom in particular. It's pumpkin pie. Okay. So we want to store text. So you've got this sentence, AMS 103 is my most annoying class this semester. How do you turn that into zeros and ones? Okay, so we heard there's a guess here of hexadecimal. Well, that's not necessarily going to give us zeros and ones. It could. But the other thing is now we have the issue of how do we do with spaces? How do we do with letters G through Z? How do we deal with capital and lowercase? How do we deal with at symbols and periods and commas and semicolons and punctuation and M dashes and N dashes? This starts getting complicated. Okay, so we had an idea?
I was going to say assign a numerical value to each number and then represent it using the numbers.
Okay, so maybe what we... Right. Well, let's see. So maybe what we can do is we can associate with each letter or number or character or symbol, whatever the case would be, a number, because there's a discrete number of letters, symbols, characters we have. And then we can convert each of those numbers to binary using the tools we've already seen. Does anybody think that seems plausible? Can anybody think of a better idea? If you can, I'm sure the computer science department would love to hear from you, because that's exactly what we do. So good job. All right. And so basically, there are several ways, but the predominant one is what's called the ASCII table. And I know this is small print on here. But what you can see, sort of, you can ignore sort of the second column, but in each one of these 4 bigger columns, what you've got on the left here is this decimal code. So notice there's just a continual number starting in this third major column here from 64 down to 95. And if you look on the rightmost part, there's a character. And so like associated with the number 64 is the @ symbol. Associated with 78 is capital N. Okay? Coming over to the very rightmost column, we can see associated with 120 is lowercase x. You'll notice there's a bunch of punctuations sort of in the upper 50s and low 60s. We've got there's our colon, semicolon, less than, equals, greater than, question mark. We have all of our numerical digits actually represented by numbers. So if we want to think about the character or the symbol 6, that's actually going to be represented by the number 54. Yep.
How come in, I think it's the
Octal.
section?
Yep.
Octal section, how come it skips 8?
Okay, so the question is in the octal section, how come it skips 8? Do you want to take a guess what octal is? It's base 8, so we can only go from 0 to 7. So basically what these two middle columns are doing is they're taking this decimal number, so like something here that's 32 to 63. The second column is converting it to hexadecimal, so base 16. And then the next column is using base 8, called octal, which only has digits that go from 0 to 8. Don't worry about those necessarily so much. But the idea here is we can take each one of these characters and give it a unique number. The computer can then store and process that. Do it. Question. So if we look over at this leftmost major column, what do you think all of those characters are that don't really appear as anything? Do we just have a whole bunch of numbers to represent nothing? Well, they're all not necessarily spaces, but they're what's called white space. So for instance, as indicated here, they actually specify that one. Look up at number 32 at the top of the second column. And the character associated with the number 32 is space. So when you hit your space bar and put a space, the computer is necessarily storing the number 32. All of the things on the left-hand column, there are plenty of other types of white space that the computers might use. Like when you hit an enter key, what does that get represented as? Well, that says a new line. It's not a space, but it's still not necessarily a visible character in the sense of a letter or a number. That's going to have its own code. I think new line is 18. I might be wrong on that. Different operating systems use different types of encodes for this. So there's a thing as a carriage return. There's a line return. There's a whole bunch of different white space elements that the computers can use, and that's what all of those 0 through 31 are. So they don't actually show up as a visible symbol, but they're used for formatting within the document. Okay, does that make sense? All right. So the ASCII stands for the American Standard Code for Information Exchange. And I just want to take a moment to specify, this table when it first came out was the ASCII code. So if you hear someone talk about ASCII, this is what they mean. Given how prolific computers have become, I think that ASCII code was introduced in the 1970s. They've done quite a bit of extension over the years, so now we have extended ASCII tables that are available for other characters or symbols. Notice there are a lot of things this table leaves out. Where's your favorite emoji in this table? It's not there. Okay. What ends up happening is there are all sorts of other tables that can give us numerical values for other types of symbols. So there's tables for doing emoji. There are tables for math symbols. If anyone's seen, math can be typeset. And we can have all sorts of Greek letters or other types of alphabets used entirely. Anybody like Dingbats, the font? Those can all get symbols if we really wanted to. Okay. And there are also plenty of other standards available for encoding non-Latin or non-Greek alphabets as well that follow the same approach. Figure out what are the characters that you need and associate with each of those characters a number. And so then when we want to convert our text to ones and zeros that the computer can process, we go through every character, give it a number, and we can convert that number to ones and zeros using the binary number system that we spent quite a bit of time talking about. So again, we spent, I don't know, one entire lecture period talking about binary numbers and 10 minutes talking about text. Any questions? We'll do an example on the next slide, but does anybody have any questions before we get there? Okay, so now we can think about going sort of the two ways. In the one way, we can say, let's convert an ASCII sequence to text. So suppose I'm going to give you the sequence of 72, 101, 108, 108, 111, 33. I know you were all able to copy down that ASCII table for the 10 seconds it was up on the slide. what message, what text do you think this represents? So how would we go about figuring this out? Yep. Well, we first want the table. Okay, so let's keep those first two digits. We've got a 72 and a 101. Okay, so what we can do is we can come back up to the table, and we can look up and see that 72 corresponds to what character? Is it H or is it capital H? Notice we have 104 tells us lowercase h. So we want a capital H. And what was the 102? Or it was 108. Sorry, it was, no, 101 was the next number. It's a lowercase e. And then we had a 108. We actually had two 108s, which would give us two lowercase l's. Okay, anybody want to take a guess what this says? It's not hello, it's hello. Because we put an exclamation point at the end. Okay? So that's all there is. So we can just take those numbers, look at the table, and convert it back to text. Okay? Yep.
For the last lesson, other pseudo standards are available for encoding non-Latin.
Yep.
Non-Latin letters and non-Latin alphabet.
Well, non-Latin letters or alphabet would be nominally the same thing. But for doing any sort of non-Latin characters, there are other standards that exist. They're just not part of the original ASCII table because that was developed in the States and we're ethnocentric. So it can, again, it depends what standard you're using. So if you're going to use something that isn't, let's say, just English, where you have here are the 26 letters and there's no accents or other things on it, you would probably just use ASCII. But if you want to start introducing accents on the characters, you're going to need another table to characterize, because you would say, well, E with one accent is going to be a different symbol. E with a different accent will be a different symbol, and so on and so forth. And so there are standards that exist for that, but they're functionally the same as this. The idea, take whatever that symbol or that character is, give it a number, convert the number. Does that make sense? Okay, so we can also then go the other way, and how would we convert mundane to ASCII? What do you think? Okay, obviously we're going to need the table again. These lecture notes will be posted so you can have the table when you're looking at your homework and all that. And I will give you the table, if it's necessary, on the quiz. I don't expect you to memorize it. Okay, so basically the idea here is we need to take all of these letters and we can look at, say, what is capital M, go to the table, and get the number. And then get what's the number for capital U, and what's the number for capital N, and put them in order. And so if we go up to do that, well, capital M is 77, and capital U is 85, and capital N is 78, and so on and so forth. And when we're done converting that, there's the string of numbers that we get to represent that word.
Are we going to end up going from words to the ASCII system, I guess decimal, and then making it to binary?
So the question was, are we going to have to do something where we have, like, here's a text, stuff of text to go to ASCII, to go to binary? Are we going to have to do that in this class? Probably not, because I'm going to assume if you can go from the text to the numbers, then I will test independently, can you go from the number to the binary? I mean, so you can see the idea of this is how it all works, but I probably would not ask something that complicated. Okay, so questions about how we do text in the ASCII table and the conversion. Okay. So then, in the last few minutes today, we can discuss how do we go beyond numbers and text. And so the one example that we're going to look at in class is this idea of images. Can computers store and process images? Yep, no problem. What are some of the challenges that we're going to have to deal with when thinking about storing an image? Yep. Okay, so how do we get certain wavelengths of light to certain numbers? That's absolutely an issue we're going to have to deal with. What are some other issues potentially that might come up? Anybody have any ideas? Okay, so the intensity of the light. So there's a whole bunch of things concerning generally color. How do we talk about color? Because how many different colors are there potentially in an image? There's an infinite number of colors. Can computers deal with infinite things? Nope. So we're going to have to talk about color in some way. If we think about having the canvas of an image, how many different points are there along that image where we might want to know what is the color at this point? There's an infinite number of points. Can computers deal with infinite things? No. So we're going to have to somehow break up that image into a finite number of points to consider. Does anybody know what those points are called? They're called pixels. Okay. And so basically, these are two of the big things. As we've said, there's an infinite number of positions, and so what we're going to have to do is discretize our picture into some finite, some discrete number of points that we want to know what's the color here. Okay? And each one of those points is called a pixel. There are also an infinite number of possible colors. Once we have that finite number of pixels, what color do we associate with each one? We're going to have to discretize our colors as well. And so these are some of the challenges when we start thinking about images that we have to overcome. If you really want more information, a course in computer graphics, something like CSE 328 will go through this in excruciating detail. We are going to do it in probably under 20 minutes, but that will not be done today. So I hate to put the big quote here, but from Wikipedia, discretization concerns the process of transferring continuous functions and models into discrete counterparts. Okay, so that makes sense. Discretization makes something that isn't discrete into something that is. Okay, so this process is usually carried out as a first step toward making them suitable for numerical evaluation and implementation on digital computers. Okay, well that sounds to be sort of what we're trying to do. The issue, though, that we run into is whenever continuous data is discretized, there's always some amount of discretization error. Okay? What that means is when we do this discretization, we take our image and we cut it up into some discrete number of pixels, are we losing some information? Yes. When we take our infinite spectrum of colors and we reduce it to some discrete set of colors, are we potentially going to lose some information? Yes. And so the trade-off here is always, we want to make that discrete set as small as possible because that makes it easy to store and process on our computer, but we need it large enough that what? When you look at the image, do you immediately notice that this is a really cut-down hack, or does it look like the real thing? You want it to look like the real thing. You've all seen the image that doesn't have enough resolution, and it's really sort of grainy or chalky or blocky or whatnot. Okay. You can detect as a human that's not right. If you then said increase the resolution, would you eventually reach a resolution where you, just sort of looking at it on your screen, would not detect the difference? Yeah. And so we need to find out what is that amount, and that's what we're really targeting. And so the difference between now the actual picture and what you see on the computer is that discretization error. Okay? And so that just sort of is the last thing, discretization often controls the amount of data to be stored. Again, the more discrete things we need, the more pixels we have, the more potential colors we can use, the more we have to store. And that means the more we have to process, which means the longer it takes Photoshop to do whatever it is you're trying to do. Okay? So to see sort of the evolution of this, you can think of our image or our picture as this 2D canvas. Okay, so we've got, sort of like the artist has their canvas, and we're going to start drawing and putting colors on it. And so, as we've already discussed a little bit, the best way or the easiest way to think about this is to divide that 2D canvas up into lots of little boxes that we'll call pixels. And what we're going to try to do is associate with each of those pixels a color. And that's what's going to get displayed on the screen or stored in our file. And so you can sort of see the evolution of different graphics as time has gone on. We're back in like 1981. He wasn't even super at that point. That's what Mario looked like. And you can see, so first of all, can you see the individual pixels in that picture? Yeah, you can see there's all sorts of little blocks. How many colors were there in Mario in 1981? There are 4. You see there's sort of the red in the overalls and the cap. There's peach for the hands, the button, and the face. There's blue for the hair, mustache, and shirt and shoes. And what's the 4th color? White for the background. Okay? And so that was basically the best that Nintendo could do in 1981. Now, why did they say we're only going to have, I don't know, maybe 20 pixels in the vertical direction and 10 pixels in the horizontal? Why did they say we're only going to have those 200 pixels? Did they maybe want to do more? Yeah, but why did they limit it 200? That's all they could handle. The classic Nintendo Entertainment System, by modern standards, was a very feeble processor. And if you had a video game and every time the screen had to redraw, it took 30 seconds to process the graphics, is that particularly good for a video game system? Where you hit the button, have to wait 30 seconds for the screen to redraw, and then you hit the button, and you're going to find you got taken up by that fireball 2 minutes ago. Okay, and so with the processor and the computing power that they had, that's the best that they were able to do. That was the trade-off. We can have 4 colors, and we can have roughly 200 pixels, and we can keep the gaming system running in essentially real time. Okay, so they found better ways to do some of these algorithms, because 1985, so now that's actually Super Mario, 1987 Super Mario 2, 1990 Super Mario 3, and the graphics are getting a little bit better. The actual image sprites are a little bit bigger. Pixels are a little bit smaller, and okay, we're still at 4 colors. Okay, that sucks. But we can get a little bit better. And what happened, notice now there's a pretty marked improvement between 1990 and 1991. What happened there? Historically, anybody who's a video game buff, and I know some of you are based on your choices of term paper, what happened? It's the Super Nintendo. So now we have a completely new piece of hardware that's essentially 10 years newer, which means it's going to have a better processor. It's a more powerful machine. Can it handle processing more data in real time? Yes. So we can have bigger images with more resolution. We can have more colors and still make the game play in real time. And so we can then progress along. 1996 is the Nintendo 64, which now actually had the power to be able to do, at least in some crude way, 3-dimensional rendering. And so you can you actually see necessarily the individual pixels on this guy? If you look real close on a good computer screen, you probably can. On this projector, the answer is no. But you can see it's 3D. 2002 is then the GameCube, and 2008 is the Wii. I haven't updated this for either the Wii U or the Switch. But you can start to see, I mean, look at now, in the 2008 using the Wii, you can see there's shading all around the face. If Mario hadn't been sleeping at night, I'm sure you could see he would have bloodshot eyes. You can actually see, different texture in the Gene overalls to represent that. All of that detail requires pixels, and it requires space to process. And so to think about that, in basically 35 years, we've gone from this tiny little sprite of 200 pixels and 4 colors to real-time being able to make Mario with studded genes. I think that's really kind of cool, that the computer power has come that far in that amount of time. But that's why the graphics get better. It's not that in 1981 they were lazy hacks and said, oh, we just don't want to take the time to do this. They didn't have the machinery. And so sort of tying it back together, that's where all of that discussion of compute power came from when we say these devices have gotten better. So I think that's probably a good place to end for today. We will pick up with this discussion and talk about some color spaces and other issues with discretization next time. Have a wonderful afternoon, and I will see you Wednesday morning.